All right, welcome back. So we are now switching over to studying the gravitational interactions of a much larger number of objects than we were studying before, the n-body problem. We will spend 3 days on this. I guess the first day here, number one, we'll be looking at some of the implications of collisions in this sort of a similar way that we've looked at Coulomb collisions for charged particles. It'll require us to look at things statistically again and look at phase space distribution functions again. But then next week in the 2 days, we will basically forget about collisions because it turns out that there are some large-scale gravitational systems. One example is our own Milky Way galaxy, where individual pairwise collisions are not that important, are not that frequently occurring. So we can use a more collisionless way of thinking about these statistics, and we'll spend 2 days on that. But yeah, collisions are sometimes important. Yes, space is big. You know, the space between the stars in a galaxy, for example, is very large. So we're usually not going to be talking about direct collisions using the colloquial definition of collision. Usually we'll be talking about collisions like we did with Coulomb collisions, you know, just these sort of hyperbolic deflection trajectories. But sometimes, and in the final video today, we will actually talk about the times when actual direct head-on collisions or glancing collisions actually happen between bodies in something like maybe a globular cluster or a protoplanetary disk. Numerically, if you want to actually study these things for research, usually if you're a theorist, that pushes you into a very computational heavy domain. N-body simulation codes are a big thing. At the bottom there, I have sort of a successive list of record-breaking codes where the total number of particles that has been able to be considered simultaneously has grown into the trillions, and soon we'll be approaching 10 trillion, I guess. You can try to verify for yourself whether this trend is keeping up with Moore's law or not. I think it's sort of in the same ballpark. I always like going way back in the history, and I was interested to find this paper from Holmberg from 1941. It's actually sort of 10 years before astronomers got access to computers in a reliable way to do simulations. Holmberg did this analog simulation. He sort of set out these 37 light bulbs on a table that could pivot around and move around. I guess it was just a 2D simulation. But each light bulb had a little photocell on it, maybe an array of them to get the light from all different angles. And he took advantage of the fact that the intensity of the light from each light bulb as measured by another light bulb dropped. The intensity drops off as 1/r², much like the gravitational force does. So the detected light tells you something about the gravitational force on these light bulbs. So they were able to learn some actual physics about large number body systems from this analog simulation. Yeah, I'll put the link to this paper in the description, and also a link to the state-of-the-art Quijote simulation as well, so you can sort of bracket the two ends of the history. Yeah, so we won't be talking too much about the numerical simulations. But there are some important things to think about when trying to do them. Getting good science out of them requires speed. If you really want to compute the gravitational force on one star from n other stars, and then you want to do that for all n stars, you can see that would have to go as n². You'd have to sum up, all the pairwise interactions. But having a code that scales as n² is probably, probably rapidly gets you out of the range of realistic computers. You'd have to wait a long time for computers to grow like that. So there are these other methods. There's this tree method. It's actually a family of different techniques, I guess, that divide up the volume into cells. And if you want to compute the gravitational force on some body, yes, you sum up over the nearest neighbors as individual bodies, but the more distant ones, you just sort of take their sort of agglomerated gravitational force for the entire cell. And that actually is much faster in terms of computer time. It doesn't go from n squared to n, but it does drop it down to something like n times the log of n, right? It's not as steeply rising as n squared, but it's more steeply rising than just n itself. Linear rhythmic, I've often heard that called. So yeah, so you need speed, and you also need accuracy in these simulations too, right? Let's say it was something more modest than a trillion particles. You know, just say you wanted to figure out, is the solar system stable over billions of years, right? So you put in, you know, the planets and a few hundred asteroids and integrate them in their orbits around the sun. If you do that over billions of years, you know, billions of orbits, small errors in the computational way of doing it can grow with time, and you really want to take the care to minimize those. So there's this whole field of designing symplectic integration methods that minimize the buildup of those errors, and you can make use of the whole Lagrangian or Hamiltonian coordinates, the p and q coordinates, to figure out the best way of doing these things and stepping them forward in time. So yeah, there's a whole bunch of different interesting ways of doing this. But in this course, we're not going to talk too much more about them, because when you get to very, very large numbers of bodies, bigger than a trillion, you really have to switch over to a statistical way of thinking about it, right? You have to think about the phase space density as a function of position and momentum and time. That evolves in the same way for particles in a plasma using the Vlasov or the Boltzmann equation. And sometimes you have to have this collision term on the right-hand side, because as we saw earlier, the force and the little f itself are correlated with each other. So treating them as their statistical versions requires this sort of leftover term. And in gravity, we have to think about this force a lot, right? Because the force is generated by all of the other, by all of the particles in the system. And, you know, even if we can ignore collisions, we still have to take account of this dependence of the force on the distribution itself, right? The force is just the minus the gradient of the potential, and you can write the potential, and we'll make use of this a lot later. You can write the potential as this integral over the volume of which there are gravitating particles. And if it's a continuous, you know, you're treating everything continuously, this is sort of a mass density. How much density per unit volume is there, divided by the mean distance between where you want to measure it and each little volume element. Of course, I'm sure you've seen how this reduces, right? If this density function is just a delta function, right? If there's just a point mass at one point in space and vacuum everywhere else, that rho is just an m times the delta function. So this integral over just rho itself is just an m. So what do you have? Minus gm over the distance to that point mass, right? And you know, we've seen how that works. But the more general version is something we have to confront when you have extended distributions of mass density. And of course, the mass density is just a moment over the f, so it's a very cyclic thing. Yes. And of course, there are places where you do have to worry about actual collisions, you know, pairwise collisions where their effect gets summed up over time, as we saw for Coulomb collisions as well. And yeah, when we actually start to think about it, we realize that there are some aspects of this problem that are a bit more difficult to deal with. You know, in plasmas, we had the Debye length, right? That was this scale over which you could stop worrying about Coulomb collisions, because bigger than that, the screening effect basically balances out all of the positive and negative charges, and there's no electrostatic forces beyond that. But gravity doesn't have positive and negative, it just has the one sign. So gravitational forces keep building at large distances, and we'll quantify that in just a minute. So yeah, so what we're going to do specifically in the next video is to start to look at these collision timescales. You know, how frequently do collisions happen? And again, we're going to have to worry about truncating these Coulomb integrals at some point. You can't truncate them at the Debye length, so you have to keep on going all the way out to the size of the system. And yeah, and I can sort of prove why that's the case by looking at sort of a toy problem here. So what we'd like to do is, if you're in a distribution of mass that's sort of evenly distributed, and you're at some test particle sort of in the middle, what's going to matter more for calculating the gravitational force on yourself? Is it going to be the nearby objects or the more distant objects? And so, we know gravity is a long-range force, so these more distant objects might be important. There's no cancellation, as I said. So let's look at this toy problem. So let's think about a uniform density distribution of stars, all with the same mass, distributed throughout space. But now let's distribute them only in this sort of cone-shaped wedge. It's not an exact cone. It's just sort of a cone-shaped section of a sphere with number density n, and the star that we would like to figure out the forces on is at the center with the same mass as all the other ones. Now, I'm creating this wedge just as a convenience so that we don't have to worry about vector forces. In other words, if we want to figure out if theta is small, the opening angle of this wedge is small, then pretty much all the forces from these other stars are going to pull our test star in the same direction, right, to the right in this diagram. If theta was big, if it goes up to 90 degrees or 180 degrees, then we'll have to worry about vector cancellation from the different directions. But here, let's keep it small. So let's just worry about magnitudes of the force in that same direction to the right here. All right. So the way we can quantify the question, right, is it the near ones that are more important or the far ones that are more important? Let's take a constant width dr for a little piece of this wedge and move it around in radius, right? And of course, we know that that as you move it out, there are going to be more stars in this wedge of constant width at a larger distance, but they're further away, so they should exert less of a gravitational pull on the test star. So let's write everything out in detail. And again, you might have seen this argument before, and it's probably not surprising what will happen. But let's figure out the force on the test star from all the stars in each wedge. And let's allow this radius to just be an arbitrary thing that you can move back and forth. All right, so the force on the test star is going to be, it's just m over r squared. If the wedge is narrow, then they're all sort of at the same distance away. That's sort of why we set it up this way. And the total mass in the wedge is going to be the total number of stars in the wedge times the mass of each star. So the GMM is basically, there's one m for our test star, and then there's an n times m for all the other stars in the wedge. Now, how do we compute the number of stars? It's just this constant number density times the volume of this piece of the wedge. How do you compute the volume? Well, it's just the thickness, dr, times the area of that polar cap of the sphere. You can do the integral over the surface of the sphere from the pole to some value theta, and then assume it's symmetric in phi. That symmetric in phi gives you the 2 pi here, and then everything else gives you the r squared times 1 minus cosine squared. All right, if you took that all the way around, it would be 2, and you would get 4 pi r squared for the total surface area of the sphere. All right, well, we have the number of stars, we have the force, we can plug that in, and again, it's not surprising, but the r squared in this geometrical factor here cancels out exactly with the r squared in the gravitational force. So the magnitude of the force is actually a constant that does not depend on the distance r, right? So distant stars contribute comparably as nearby stars to the gravitational force when you're looking at it this way here. Yeah, so this just is another way of thinking about the fact that we really have to integrate over the entire system to take into account all of these things. Yeah, I already talked about the fact that we didn't take the theta to be very big just so we didn't have to worry about the vector effects. But yeah, I mean, in reality, we're not sitting at the center of an exact spherical distribution where everything is evenly distributed. If there's asymmetries, you can think about them in terms of wedges like this. So yeah, that's our moral. We do need to think about these distant interactions, which means, we can't cut it off at a Debye scale Vmax. We have to take into account everything all the way out to the size of the system. And in the next video, we will do just that.